Welcome back, folks. This is the next video in chapter 10 of our DB2 course, where we discuss the matching of queries and indexes. The last video has talked about composite indexes and how it's very clever to put the most selective columns that support the most selective predicates first in a composite index. Have them first in this concatenated key that makes up the composite key in the multidimensional index. Okay, so this video will talk about a technique where it really makes sense to put the low selectivity columns first in this composite B+tree. Okay, so this of course does not render everything false what we've said in the previous video. This is just a different use case, one particular use case in which you have to reconsider column order in your composite keys. This particular use case are the partitioned B+Trees. This is a very nice, very elegant technique to support, to sufficiently support bulk inserts of large batches of rows into tables and of course in the indexes that are associated with these tables. Right, so if you follow this particular technique, you can expect these inserts, in particular the B+tree inserts of these large bulk inserts, to be performed more quickly. And there's a trade-off there. I will explain where the trade-off lies, but it's very elegantly implemented and it really shows some intricate and some deep knowledge about the internals of B+trees. And it's no wonder that this technique has been described and made popular by no other than Götz Graefe, which is one of the big brains, which of the really long-time contributors to relational database technology, in particular to the internals of B+trees and variations of B+trees. So if you come across Götz Graefe, you should buy him a beer. He has made significant contributions, countless contributions to B+tree technology. All right. Okay, so let's see what these partitioned B+trees are all about. So we would like to operate on a table, and indeed the table would only look like this. Of course, it could have more columns than just this column C1, but for the demonstration on this slide, this should be sufficient. This would be the actual data that we try to play and operate with. Okay, in the partitioned B+tree technique, we would make this table a bit wider. We would add an additional column P here, the so-called partition column. All right, a partition column. In the beginning, we would just set this entry in the partition P column to all 0. Okay, so the information content in this particular table would not change. It would just be a table that represents this particular data, but all of the rows are being augmented with their partition ID, which is just all 0 here. 0 would be the main partition, the default partition in a sense, but we could pick any value here, but 0 is just a convention here. All right, so we would of course operate on this table. We would perform queries on this table and would expect these queries to be fast. All right, but then at one particular point there would be a bulk insert. A large number of additional rows are being inserted into this table. And well, insertions into such tables, of course, means maintenance of the associated indexes. All right, so that would mean start from the root of the B+tree to insert a new row. Try to find the correct spot for that row inside the sequence set, insert it there, maybe split all the pages up to the root if we are out of luck, and so on and so on. You know the B+tree maintenance and insertion procedure. We have also described the fast path, the possibility to have fast bulk loading in B+trees, but this all hinged on the condition that the new rows, that the insertions into the B+tree have to occur at the very right-hand side of the sequence set. We have to insert rows that are larger than any rows that we have seen so far. If we find ourselves in this particular situation, then we can use the fast path, the fast bulk insertion into B+Trees. Okay, so if this is the actual data that we need to insert into our table, then let's just augment these new rows with a p-value, with a partition value of 1 here. Okay. Since this defines the key, the composite key in our B+tree, okay, so the composite key order, I didn't say this explicitly, but the composite key order, of course, is the P, C1 order. All right. Okay, so if we insert these new entries into this B+tree, then they will be placed at the very end of the sequence set. They will be inserted at the right-hand side of the sequence set because their key values will be larger than anything that we have seen so far. The P value here, the first part of the composite key uses all ones in this particular column. These all ones make all these entries larger than any entry that we've seen before. So they have to be inserted at the very end, as shown here, of the sequence set. And of course, we can use the very fast bulk insertion procedure to do just that. All right, so we can expect this batch insert to be very quick and very efficient. We could then continue to perform queries over the underlying table. This would be the composite index that we can use in that. Okay, so once the system has performed these inserts, we can continue with normal operation. All right, but at one particular point, maybe another bulk insert, another batched insert of rows is going to come. Well, and we would assign the next available partition ID, 2 maybe. Any partition ID that is larger than anything that we've seen so far would work. Okay, the bulk insertion, the batched insertion, will again hit the right-hand side, the very end of the sequence set. Again, we could use the very fast and efficient fast path in the B+tree insertion algorithm. The bulk insert would be efficient and append the rows at the end of the sequence set. All right. At one point, we may find the system to be idle or to be in maintenance mode. At this point in time, we could decide to set all these partition IDs that are non-zero. So of all the rows that have been inserted recently, we could decide to update them and set them to 0. So changing them from 2 to 0 or from 1 to 0, from 1 to 0. All of this could happen. At this particular point, at this update time, the B+tree maintenance will of course sort the rows, into their correct positions according to their C1 value. The P value will be all 0. So this will not influence sorting order. The sorting order will only be based on these C1 columns here. Okay, so setting the P value from 2 or 1 or any non-zero value to 0 will perform a merging of these partitions, into the overall row data of the underlying table, or the underlying sequence set rather. Okay. Yeah, so I think this is a very elegant technique to postpone this merging and reorganization effort in the B+tree by using these partition IDs, and then have full control over the point in time where we set the partition IDs to all zeros, and then invest the time in the reorganization of the B+tree and the reorganization of the sequence set. For some workloads, this might be just the right thing to do, and it's very easily expressed and very elegantly expressed actually on the side of SQL. So let's switch over to the SQL terminal here and let's get cracking. All right, so we would just simulate the situation on the slide by first providing a table with the real workload that we care about. So a table with, say, A, B, C columns here. Okay, so no partition column yet. Let's do that. So this is the table, and we would normally just operate over this particular table. What we will now do is we add another column, the partition column P. Okay. We will add this column to all the rows in the table, so that applications are not being bothered with assigning partition IDs here at this particular point. We will just set this column to a default value of 0, and then also check or establish a constraint that will keep applications from later assigning partition IDs that are less than 0. Okay, so but let's do that. Okay, so to get things off the ground, we would just start with the insertion of a first batch of rows of these 1 million rows here. You see that I'm only specifying the ABC column values here. The default 0 will lead to a table in which all of the rows are augmented with a fourth column that is automatically set to 0. So let's do that. So that's 1 million rows that are being inserted into the parts table now. This is a 4-column table. Okay, wait. Okay, done. Right. Okay, so now it's time to create the composite index. So we will we expect that the system or that the workload will feature queries that are focusing on the A column here. All right. But we will build a B+ tree on the P, A concatenation or combination of columns. All right, so the P, that's very important, is first here. It will determine the sort order so that we can really sort the rows by their partition, in a sense, in the sequence set. So let's do that. Let's even reorganize the underlying table according to this partitioning and then analyze the situation. So let's do all of this, creating that index. Okay, clustering the underlying table and analyze all the stuff. Okay, so let's look at the table and maybe only at the first 10 rows or 20 rows. Okay, so these are the ABC values. So this is the real workload, the real meat of the table. Okay, the payload, and this is the partition column. Of course, it's all 0 now. So all of the 1 million rows are currently part of the first of the default of the main partition. Okay, right. And well, yeah. So since the A column has been the second criterion here for index organization, we see that this cluster table, really freshly clustered table, if we just dump the rows in heap file order, we find ascending A values here. All right. But of course, this is the guaranteed order of P and A values in the sequence set of the parts PA index. Okay, so everything has been set up just like on the slide. So now we could perform queries on this parts PA table, but at that particular point there would be the first bulk insert. So we would insert another 1 million rows into this particular table. All right, so that this goes fast and that we hit the bulk load fast path of the B+Tree insertion code in our system. We will make sure that we insert all the payload here, all the payload, the ABC column, but also assign a partition value of 1, of something as is larger than what we have seen so far. Okay, so let's do that. All right, so that went reasonably fast. Okay, insertion has been done. Okay. And well, continue the operation of the B+Tree. Currently, the sequence set has not been reorganized. The rows in partition 0 and in partition 1 are separated. Okay, another insertion, bulk insertion is hitting us. Of course, we will do that with the next larger partition ID of 2. Okay, done already. So this is the current state of the table. We have the 0s, the 1 and the 2 partitions now. Okay, so now it's time for downtime, for idle time, and we could now reorganize the tables such that the sequence set indeed reflects the order of the rows in a column order, all right, and set all the partition values to 0. Everything from then on is considered to be the main or default partition. And we can easily do that. We could just set the partition ID to 0. For example, for all the rows that have been inserted into partition 1. Okay, so that would be a partial reorganization here. Later on, we could decide to do the same thing for all the rows in partition 2. So if the entire merging and reorganization of the sequence set is something that we don't want to suffer from at this particular point, then we can do that partially. That's very nice. A benefit of this technique. Of course, we could just change this predicate and say anything that is not currently part of the current partition, of the current main partition, I'm sorry, should be merged into the main partition. This could be possible, or we could specify something like this. Explicitly list particular partitions that we are currently interested in to merging. So there's really some leeway, some flexibility on when to merge what. So I think this is a very beautiful technique. Okay, so this is the original state. Let's perform the merging of partition 1. Now some B+Tree reorganization has happened, and the second partition is merged too. Now everything is in the default partition. And well, we could continue querying and of course accommodate new partition inserts with partition IDs 1 and ascending from now on. All right, so that would be the partitioned B+Tree technique. I think it's just beautiful. Okay, and to summarize all the SQL code that would make up this partitioned B+Tree technique, I have added slide 12 into the slide set. What you see here is exactly what we've just performed on the PostgreSQL terminal side, so nothing new to learn here. If you want to operate such a table T under the partitioned B+Tree technique, of course, what's partitioned here is the ranges of the sequence set in the B+Tree that we are building. Well, then just alter the table and add a new column P, the partitioning number, to this table, and then build a B+Tree according to this concatenated key. All right. Right. Then later on, perform inserts regarding particular partition IDs that are ascending. So you have to actually do the bulk insertion using the B+Tree insertion fast path. And when time comes, perform merging so that everything is in proper C1 order. All right, and so that you're prepared for upcoming merges in the future. And of course, there's some flexibility there. We have all discussed this already. So that's partitioned B+Trees. It's a technique so nice that I needed to show it. And actually, it's a nice counterpoint to the rule of thumb index for high selectivity first. Grust would say, yes, but in some cases, low selectivity wins. For example, when it comes to partitioned B+Trees. All right, that's about it for this video. See you soon, and I hope you will be around. There is more index goodness to come. Bye.